Tonight, in the first week of December 2025, something very quiet and very strange is happening far beyond your sky. NASA's latest trajectory update for 3I Atlas now shows an interstellar object, not from our solar system, slowly lining up with a tiny gravity keyhole at the outer edge of Jupiter's domain, not crashing into anything, not threatening Earth, just drifting with a level of precision that ordinary comets almost never show. And you, sitting here at the end of a long day, have decided to press play on a title that promises to make sense of that. 3I Atlas is quietly lining up with Jupiter's gravity keyhole. Science for sleep. You did not click because you wanted to be scared. You clicked because you were curious. You want to know what it really means for an object from another star system to slide toward a narrow doorway in Jupiter's gravity. And you want to hear it explained in a way that lets your shoulders drop, your breathing slow, and your mind stretch without anxiety. You want real data, calm speculation, and a sense of perspective that lets you fall asleep, feeling a little smarter and a lot more at peace. So that is what you are going to get tonight. Over the next hour and a half, you will hear three things. First, what the latest observations actually say about 3I Atlas. The numbers, the angles, the strange consistency in its path. Second, what serious scientists are quietly debating about this object, from NASA's cautious models to Avi Loeb's more provocative questions. And third, what all of this really means for you, for Jupiter, and for your place in a universe that is far more ordered and far more reassuring than the headlines ever suggest. For now, you can let the rest of your day go. The emails, the news alerts, the mess of human noise can wait. Right now, your attention is leaving the room and moving outward, past the clouds, past the quiet blue of the upper atmosphere, past the orbit of the moon. You follow an imaginary line that passes Mars, crosses the asteroid belt, and continues until it reaches the great, invisible bowl of Jupiter's gravity. Somewhere at the edge of that bowl, an object no one knew existed a decade ago is on a path that should have been random, messy, and full of noise. Instead, it looks almost clean. To understand why that matters, you need to rewind just a little. For 35 days this autumn, 3I Atlas disappeared behind the sun from our point of view. During that time, astronomers could not track it directly. They could only predict where it ought to be when it came back into view, based on everything we knew before it slipped behind the glare. Those predictions were good. They were the kind of careful work JPL has done for decades. But they were still predictions, and predictions always wait for reality to either confirm them or quietly correct them. When Atlas finally emerged again, faint but clear against the star field, reality did what it always does. It added a detail that no one had written into the script. The object was not exactly where the models had placed it. It was off by a small amount, not a dramatic amount, not an amount that would make a sensational headline. Just enough to make careful people sit up a little straighter. Just enough to make someone on a late shift somewhere say, "That is interesting." The weird part was not the fact that it was off. Comets are notorious for small misbehaviors. Ice heats, gas vents, jets of vapor push gently in uneven ways. The weird part was the direction of the deviation. Instead of drifting in a messy, somewhat random pattern, 3I Atlas shifted along a line, a clear, repeatable line. And that line nudged it closer to a corridor of space that leads toward a gravity keyhole at the edge of Jupiter's Hill sphere. You do not need the equations to feel the weight of that. Imagine throwing a coin across a football field and watching it land gently on its edge. Imagine sailing across an ocean and passing through a gap in the rocks only a few feet wider than your boat, without ever touching either side. That is the kind of precision we are talking about when we say that an interstellar object is quietly lining up with a gravity keyhole around Jupiter. This is where your mind starts making connections. You remember the other interstellar visitors you have heard about in recent years. The strange elongated object called Oumuamua, the almost perfectly clean comet Borisov. Each one was odd in its own way. Now you are being told that the third visitor, Atlas, is not just odd. It is heading, slowly and calmly, toward the most strategically important planet in the outer solar system, and toward a very specific region of that planet's gravitational influence. It is normal, at this point, to wonder whether you should be worried. You are old enough to have seen your share of scare stories. You have heard every overblown asteroid headline. You have seen thumbnails with red arrows pointed at Earth. Part of you clicked this title to see if this was one more of those. Tonight, you get to let that part of you relax. There's no impact coming, no extinction event, no secret threat that someone is hiding from you. The story of Three-Eye Atlas and Jupiter is not a story of danger. It is a story of precision. The value of the story, for you, is not in fear. It is in understanding. There is something satisfying about knowing that, while you go about your life on this small blue world, there are objects from other star systems passing through your neighborhood, following the rules of gravity with a grace that almost looks like intent. There is something calming about realizing that you live in a universe where even the strangest events still obey deep, consistent patterns. Tonight, you are going to follow those patterns. You are going to learn why December 19th is the night everyone will be watching. What might happen when Atlas reaches Jupiter's region on March 16th, and how a narrow gravitational doorway can change the fate of a visitor from the stars. You are going to hear the calm voices, not the loud ones. The careful models, not the clickbait. And as you listen, you will feel that familiar, welcome feeling that you get when a complicated subject finally starts to make sense. You press play because you wanted more than a headline. You wanted context. You wanted a story that treats you like an adult with a curious mind and a tired body. Someone who wants to fall asleep, not by escaping reality, but by understanding it a little better. So lie back, let your eyes soften, let your thoughts drift outward, and follow this small, distant traveler as it returns from behind the sun with a path that is just a little too straight to ignore. When Atlas returned, something was off, and that small difference is the door into everything you are about to hear. There is a night circled quietly on astronomers' calendars, and it is not a date anyone on the news is shouting about. It is December 19th. Not a deadline, not an alarm, just a night when the universe briefly gives you the best possible vantage point on something very small and very far away. On that night, the geometry between Earth, the Sun, and Three-Eye Atlas lines up in a way that lets you see this interstellar visitor more clearly than at any other time in this phase of its journey. No sirens, no red arrows pointed at Earth. just a rare moment of clarity in a sky that usually keeps its secrets half hidden. On that night, Atlas reaches an optimal distance for observation from Earth. It is far enough away that it is not washed out by glare, but close enough that its motion against the background stars can be measured with surprising precision. The sunlight that hits it bounces toward us at just the right angle, giving it a temporary lift in apparent brightness. Astronomers call this a favorable phase angle. You do not have to remember the term. What matters is the effect. For a short window of time, the faint dot becomes a little sharper, a little easier to track, and every image taken of it becomes a little more meaningful. This is how you turn a vague worry into something solid and harmless. You measure. December 19th is the night when the guesswork that built up while Atlas was hidden behind the sun can finally be replaced with new numbers. If the path you heard about earlier was just a random quirk, tonight will show that. If the gentle drift toward Jupiter's gravity corridor is real, tonight will show that too. There is no scenario here where a new line of data suddenly points Atlas at Earth. That possibility is already off the table. What changes after this night is not your safety. What changes is your understanding. You might picture this as something happening far away in some sealed control room, but that is not what this night really looks like. Tonight's seat is shared. In one place, a cluster of monitors at JPL glows in the dim light as orbit specialists feed new measurements into their models. In another, a data stream from ESA's Gaia mission refines the exact positions of the background stars so that even a tiny pixel shift in Atlas's location can be trusted. And in countless quiet backyards, people very much like you have set up small telescopes and tracking mounts, letting their cameras run while the rest of the neighborhood sleeps. Some of the data that shapes the next chapter of this story will come from observatories with multi-million-dollar budgets. Some of it will come from a folding chair and a thermos on a cold patio. The reason this night is special is that three separate factors all align at once. The timing is right because we are just coming out of a long period when Atlas was invisible behind the sun. The viewing angle is right because the Earth-Sun Atlas geometry turns the object just enough for its reflected light and its motion to be enhanced as seen from here. And the distance is right because Atlas sits in that sweet spot where it is neither too close to be overwhelmed by glare nor too far to be useful. Any one of these factors by itself would make for a decent observing run. All three together make December 19th the night that will anchor everything we say about Atlas between now and March 16. That is the quiet countdown you are part of now. What we measure on this night will shape every prediction we make about Atlas's path to Jupiter. The orbit fits that come out of these hours will determine whether scientists can say with confidence that 3I Atlas is truly inside the broad gravity corridor that leads toward Jupiter's keyhole, or whether it is drifting away from that path. If tonight's data pulls the solutions toward that corridor, then the keyhole stops being just a theoretical possibility and starts to look more like a potential destination. If the numbers pull away, then we still learn something important. That even a precise-looking deviation can turn out to be nothing more than a temporary quirk. There is a certain satisfaction in knowing that you and thousands of others around the planet are watching the same quiet event for the same calm reason. All eyes on the sky tonight does not mean fear. It means curiosity, coordinated. It means that for once, instead of being pulled in 100 directions by unrelated distractions, the scientific world and a small, attentive slice of the public is pointed at one tiny moving point of light, asking the same simple question: is this path as straight and deliberate as it looks? Or is it just a brief illusion of order in a chaotic system? You do not have to do anything to be part of this except listen and imagine. You picture Atlas out there, a small visitor from another system, crossing the invisible boundary where our instruments suddenly sharpen their view. You picture the data flowing in, the models tightening, the blur becoming a line. Tonight does not change your world. It changes how clearly you can see a story that was already unfolding. Tonight gives you clarity, the one thing you did not have for 35 days while Atlas moved behind the sun, silent and unseen. And once you know where Atlas is truly heading, once the corridor is either confirmed or ruled out, the next question becomes the one that lingers a little deeper. If this interstellar object really is lining up with Jupiter's domain, why that place? When the new post-conjunction data finally settled into JPL's orbit models, something became clear in a way it hadn't before. Atlas was not just wandering back into view. It was following a trajectory that looked unusually clean, unusually steady, and unusually aligned with a corridor of space that most natural objects miss entirely. JPL's latest fit places Atlas on a path that is only slightly offset from the pre-conjunction prediction. Yet that small offset carries enormous meaning. The object sits exactly where it should if it had experienced a very subtle push while behind the sun, just enough to tilt its vector toward Jupiter's gravity corridor, but not enough to produce the messy, chaotic motion that cometary outgassing usually creates. You see the shift in 3 numbers, the gentle nudge along the A1 radial coefficient, the faint sideways whisper in the A2 transverse term, and the almost non-existent vertical drift in A3. These 3 tiny accelerations would normally make a comet dance unpredictably. Here, they form a line. This is why scientists are paying attention. If Atlas were behaving like a typical fast-moving object of ice and dust from deep space, its path after conjunction would be wider, noisier, more erratic. But as the new data comes in, the vector deviation is so clean, it almost looks curated. You can picture the object like a small boat drifting through a wide ocean, yet somehow sliding exactly between 2 buoys with barely a degree of error. The universe rarely draws lines this straight. To make sense of why this straightness matters, imagine Jupiter as a massive invisible mountain rising out of the flat plains of space. Most objects approaching it from afar feel that slope, just a little. They slide down the mountainside, pick up speed, curve, and then slingshot away again. That is how gravity wells work. They bend motion the same way a slope bends water. But a small number of objects approach the mountain just right, skimming the very edge of the slope without falling into it. They follow a contour so narrow, you could spend a lifetime throwing stones and never land one there twice. That narrow contour lies inside Jupiter's hill sphere. the enormous bubble of space where Jupiter's gravitational pull dominates over the sun's. You do not have to imagine equations to picture it. Think of a sphere 52 million kilometers wide, big enough to fit our entire inner solar system inside it, but made of nothing but gravity. Inside that sphere, Jupiter is the boss. Outside it, the sun takes over. And at the outer edge of that boundary is a ridge, a thin gravitational seam, where the pull of Jupiter and the pull of the sun almost balance each other. On that seam lies the keyhole. A gravity keyhole is not a hole at all, but a narrow invitation. It is the place where a passing object can slip between forces with just the right momentum, allowing Jupiter to redirect its path in a predictable way. Too far left? It misses. Too far right? It flees. Right down the middle? The path bends in a way that changes the object's future entirely, without touching it or slowing it down. The keyhole is not large. In celestial terms, it is microscopic. If space were the size of Earth, the keyhole would be the width of a leaf. Hitting it by accident is so unlikely that JPL once compared it to throwing a pebble from one coast of the United States into a coffee mug on the other. This is where the numbers become astonishing. If Atlas were moving purely by chance, just a natural object on a natural path, the probability of it lining up with this keyhole is estimated at roughly 1 in 26,000. A coin doesn't just land on its edge. A marble doesn't just roll into the one groove in a parking lot. And a comet from another star system does not usually approach the edge of Jupiter's Hill sphere along a vector so smooth it could be drawn with a ruler. But here is where things become genuinely interesting. The shift toward the corridor may have begun behind the sun in that 35-day window when no one could watch. Small asymmetric outgassing events, jets that release gas from one part of the surface more than another, can push an object slightly sideways. Normally, those pushes are ragged and chaotic. But if Atlas experienced them in a particular pattern while obscured from view, they could leave a signature in the vector we see now. And that signature is exactly what shows up in the new data. Not a messy wobble, but a subtle drift that nudges Atlas right into the corridor leading toward the keyhole. This is what surprised scientists the most. Natural objects, especially icy ones, almost always behave a little badly. They twist, they flare, they get unpredictable when heated by the sun. Atlas, on the other hand, is behaving as though it's stabilized, like something that either hasn't outgassed much at all or outgassed in a way that produced a coherent push instead of chaos. That does not imply anything unnatural. It just means we are watching something rare. A visitor from another star system is threading a path that most comets could not hold for more than a day. And that is where your curiosity sharpens. If this object truly continues along this line, if the drift remains this orderly, then Jupiter may not merely deflect it in March. Jupiter may collect a piece of it, a small fragment, a grain of dust, something small enough to fall into a new orbit while the main body flies on. It would not change anything for Earth, but for science, it would be a gift. This is the heart of the story, a natural object doing something exquisitely unlikely. A 1 in 26,000 alignment unfolding in slow motion across months, across millions of miles, across a cosmic mountain we cannot see. JPL's navigation lead put it in the simplest possible terms. Random trajectories don't graze hill spheres like this. Which brings us to the obvious question: why Jupiter? If you have followed comets for any length of time, whether casually through news headlines or more seriously through backyard telescopes, you know that they are not tidy travelers. A comet is a loose, fragile object, a mixture of dust and volatile ice. When sunlight hits it, the surface vents gas in unpredictable ways. Those jets push in different directions at different times, creating tiny but persistent forces. That is what astronomers call outgassing, and it is the reason most comets never stay perfectly on track. A slight push here, a little flare there, and the trajectory wobbles. The object rotates irregularly, the direction shifts slightly, and the tail broadens and disperses as material drifts unevenly away. Even the anti-tail, when visible, tends to appear faint, wide, and inconsistent over time. That is the normal pattern. It is the way comets behave when they are warming, cooling, and swinging through the changing geometry of the solar system. It is messy in a predictable way. You expect jitter. You expect noise. You expect small but noticeable deviations that accumulate over days and weeks. That is what nature tends to produce, a kind of controlled chaos. And then you look at Atlas, and the pattern does not match. The new vector data shows a shift, yes, but it is not random. It does not bounce. It does not wander. It points. Each change in direction lines up with the next, forming a sequence instead of a scatter. The object appears to accelerate slightly in ways that match the A1 radial behavior of outgassing, but without the disorder that usually accompanies it. The A2 transverse term, which often reveals sideways nudges, shows a whisper of motion, but not the noisy, uneven mix you expect from a warming comet. Even the A3 vertical term, usually the most chaotic, comes in nearly flat. The trajectory fit that JPL publishes, the result of thousands of iterations, comes out low noise, stable, oddly clean. This is the first sign that something statistically weird is happening. Not unnatural, not impossible, just unusual. Atlas is acting less like a dusty object being kicked around by sunlight, and more like something receiving a series of soft, consistent nudges. It is not following the classic personality of Borisov, the icy comet from another star that shed material in unpredictable bursts. And it certainly does not behave like Oumuamua, which tumbled in a bizarre, elongated shape and accelerated in a way that baffled half the astronomical community. Atlas, instead, is calm, almost disciplined. Astronomers have a name for what they see in the data, a clean vector anomaly. It is what you get when a series of micro-adjustments all line up in the same general direction. If you imagine a marble being tapped on a table, each tap coming from a slightly different angle, the marble will wander. But if every tap, even the smallest ones, nudges it in the same line, the marble will drift steadily. That is what makes Atlas stand out. The universe usually taps from every direction. Atlas looks as if it is being nudged from one. This brings us to a point that might surprise you. If the deviations were random, the data would show a wide distribution of angles. Chaotic systems create broad noise patterns. They do not create clean sequences. But Atlas's deviations, small as they are, cluster tightly together. They align. And when deviations align, statisticians pay attention. One researcher described it this way: statistically unnatural, but physically possible. A perfect phrase for an object that behaves like a coin, that lands not on heads or tails, but right on its edge. You can picture it more simply. A typical comet is like a stone being blown around by gusts of wind. It jerks, it tilts, it rolls. Atlas is more like a smooth glass bead sliding across a polished table. Not because something is pulling it with intention, but because the forces acting on it are combining in a surprisingly coherent way. You are watching a natural object, yes, but one that is moving through space with an elegance comets rarely show. This is where anomaly fits into the story. In science, anomaly does not mean mystery beyond explanation. It means interesting deviation that deserves attention. Every field has them. Every long-term data set reveals them. Anomalies are not threats. They are invitations. They tell you that something is happening that does not match the usual template, and they ask you to look more closely, not with fear, but with inquiry. And that is exactly what this moment offers: the recognition that precision itself can be unusual. Comets are chaotic creatures, and chaos rarely produces a line. And yet, Atlas is drawing one. A straightness that should be noisy. A sequence that should be scattered. A level of stability that makes seasoned astronomers pause. Not because they think something impossible is happening, but because they are watching a natural event acting with a degree of order that nature seldom displays at this distance from the sun. Harvard's submillimeter array team put it plainly: the noise level is surprisingly low for an active comet. Avi Loeb phrased it differently: a straight trajectory in a chaotic system is already a message. Not a message in the dramatic sense, but a message in the scientific one. The universe telling you that the usual rules are still in play, but this time they have combined into a shape you do not see often. And as intriguing as this trajectory is, it is not even the strangest part of the story. Because behind this object, faint and razor thin, lies a line of light that raises even more questions than the path itself. But the trajectory isn't even the strangest part. The strangest part is the line of light behind it. If the trajectory of Atlas is unusual, then the line of light behind it, the anti-tail, is the part that makes even experienced observers pause and stare a little longer. Anti-tails are not new in astronomy. They happen when sunlight reflects off dust that spreads out along the orbital plane, creating the illusion of a tail that points forward instead of backward. It is a geometric trick. Technically speaking, a projection effect that only appears under certain viewing angles. When they do appear, anti-tails tend to be faint, wide, and short-lived. They smear across the sky like a soft brushstroke, barely visible unless the comet is already bright and the observing conditions are perfect. Most fade within a few days. But the anti-tail of Atlas does not behave like that. Not even close. Instead of a wide smear, the anti-tail is narrow, almost impossibly so. In sharpened images, it looks like a thread pulled taut across the darkness. A line as thin as a needle, stretching for hundreds of thousands of kilometers. It has been visible for weeks now, holding its shape in a way that dust structures almost never do. The collimation, the degree to which the particles stay parallel, is extraordinarily high. And unlike a normal dust tail, which bends under the pressure of the solar wind, this one stays stiff. It does not ripple. It does not fray. It does not sag or bend the way a natural dust structure should. It simply remains a straight, unwavering beam of reflected light. Some of the best data comes from Hawaii, from a telescope in Honokaa that has been running AI-based deconvolution to sharpen faint structures. The images it produced show a razor-straight filament that looks almost drawn. Subarc second details confirm that the line is not just an artifact or a blur. Observers in the southern hemisphere, using entirely different instruments, captured the same structure from different angles. The match between the two data sets is nearly perfect. When unrelated observers on opposite sides of the planet record the same phenomenon, you know it is real. And the details are, by any standard, impossible to ignore. The line is too thin for typical dust dispersion. If the particles were light and varied in size, as most cometary dust is, the structure would widen and blur within hours. Instead, the width remains consistent. This implies that the dust grains, if they are dust grains at all, must be unusually heavy and uniform. The anti-tail is also stable in direction. It is not fully aligned with the normal tail, and yet it does not drift as the comet rotates. Most puzzling of all is its ability to survive the solar wind without distortion. A line this thin should not survive the solar wind. That is the sentence more than one researcher has written in their notes. When something persists in a place where nature normally erases detail, scientists begin proposing possibilities. The mainstream explanations, the ones you hear in quiet discussions between planetary scientists, include the idea that Atlas may contain a fragment of metallic core material from a shattered rocky world, something that releases dust of unusually high density. Another idea suggests that the dust could be composed of chemically heavy particles that naturally resist scattering. A third idea speculates about plasma interactions unique to this object's composition, producing a beam-like illusion. Those theories are cautious, grounded, and physically consistent. But when a structure is this narrow, this persistent, and this unlike anything typically seen from a natural comet, other possibilities inevitably enter the conversation. Not loudly, not sensationally, but with the calm tone scientists use when acknowledging what they cannot yet explain. Some describe the anti-tail as collimated, a term usually reserved for beams of particles or light that have been shaped or constrained. Others wonder whether an internal structure within Atlas could be producing a steady flow of material in a single direction. And a few observers note that the leading edge of the line behaves almost like a guided reflection, as if the particles were emerging from a stable orientation rather than a random patch of melting ice. These alternative ideas are not claims. They are simply acknowledgments that the observed line does not resemble typical comet physics. And unlike the trajectory data, which NASA highlights openly, the anti-tail is something the major agencies speak about only lightly. It is the amateur astronomers, the deep sky photographers, the independent observatories who emphasize it the most. They are the ones stacking hundreds of exposures, subtracting noise, teasing out details. They are the ones noticing that the line remains the same night after night. All of the evidence comes from optical data, images, not radar, not infrared, and those images are remarkably consistent. But the most important connection between the anti-tail and the broader story is this. A stable anti-tail makes trajectory measurements far more precise. When the dust flows in a clean plane, when the line stays steady, astronomers can use it to infer subtle changes in the object's motion. It becomes a ruler, a reference, a visual footprint of the forces acting on Atlas. Every day that the anti-tail remains coherent, the orbit models become more confident, and every update reinforces the same conclusion. Atlas is moving in a remarkably straight line, a line that points, ever so quietly, toward Jupiter's gravity corridor. You are watching something rare, a natural object traveling in a way that feels almost unnatural. A filament of dust behaving like a drawn line, a visitor from another star system, leaving behind a signature so fine that only patient observers notice it. This is the kind of detail you do not get from headlines. This is the kind of detail you hear when you settle into the night and let someone walk you slowly through the sky. Avi Loeb once said, "If you forget the label comet and describe the behavior, it sounds engineered." An ESA image analyst put it more gently. This anti-tail is too coherent for typical dust. You do not have to jump to conclusions. You only need to understand why scientists, amateurs, and careful observers find this structure so captivating. Nature can produce strange things, but not often, and rarely with this level of precision. And while the anti-tail raises eyebrows, the bigger question is, why is Atlas aiming for Jupiter? When you look up at the night sky, every point of light seems simple. But behind the scenes, behind the headlines, behind the carefully worded press releases, there are always two conversations happening. One is the official explanation, measured, conservative, designed to avoid overstating anything. The other is the deeper scientific debate, where specialists argue over the meaning of small deviations, subtle anomalies, and patterns that might matter or might be nothing. Atlas sits right at the center of that split. Not because anyone claims it is artificial or dangerous, but because its behavior is unusual enough that two respected schools of thought are interpreting the same data in different ways. On one side is NASA, representing the mainstream consensus. To them, Atlas is exactly what it appears to be, an interstellar comet, the third one we have ever observed. They see its anomalies, its clean vector drift, its unexpectedly stable anti-tail, the lack of chaotic motion, but they interpret all of them through the lens of natural processes. Outgassing can create small accelerations. Geometry can make dust appear more coherent than expected. A thin anti-tail can be produced by heavy or uniform grains. And a straight path can happen when the rotation is slow or the jets fire from favorable regions. To NASA, none of this contradicts the basic identity of Atlas. It is a comet, behaving a little strangely, but still a comet. And from NASA's perspective, there are no techno-signatures here. No signs of engineered propulsion, no signals, no energy patterns that require anything beyond known physics. Their view is grounded in caution, experience, and the knowledge that extraordinary explanations require extraordinary evidence. The official updates emphasize what fits the comet model: and leave out anything that raises questions without answers. They do not highlight the anti-tail. They do not discuss the consistency of the vector drift. They do not mention the narrow approach toward the gravity keyhole. These are details that, while real, would distract from the clean narrative they want the public to understand. On the other side of the conversation is Avi Loeb, whose work focuses on anomaly science, the branch of astronomy that investigates the outliers instead of smoothing them into the model. When Loeb looks at Atlas, he does not see one anomaly. He sees several, all occurring at once. A trajectory that is too straight, a dust line that is too thin, a vector drift that is too consistent, a sequence of behaviors that align with a corridor entry pattern rather than a chaotic natural path. Loeb does not claim that Atlas is artificial. He simply argues that the anomalies deserve open discussion, not quiet omission. Loeb's point is simple. Show anomaly, let science debate. He believes that when an interstellar visitor behaves in ways no previous comet has, the scientific community should bring every expertise into the conversation. Dynamicists, plasma physicists, image analysts, and anyone with the right tools to evaluate the data. He has openly suggested that NASA should invite specialists from outside the core mission teams to the briefings. Not because NASA is hiding anything, but because broader scrutiny reduces the risk of overlooking something important. The interesting part is not the disagreement itself, but how both sides are using the same information. NASA believes the anomalies are explainable within the comet framework. Loeb believes the anomalies deserve more attention because ignoring them narrows scientific understanding. Neither side is accusing the other of dishonesty. Both sides accept the data. The difference lies in interpretation. Whether the anomalies are simply quirks or meaningful signals of unusual behavior. There is also a subtler layer to this conversation. NASA's public-facing communication tends to focus on what they are certain about, not what they are still exploring. That is why you will not hear much about the keyhole trajectory in official statements. It is why the consistent vector drift is not highlighted. NASA avoids saying anything that could be misunderstood or taken out of context, even if that means not mentioning details that specialists privately discuss. Loeb, meanwhile, is not constrained by the same communication strategy. His job, as he sees it, is to point at the corners of the data NASA leaves unlit. This is what real scientific disagreement looks like. Not shouting matches or sensational claims, but two perspectives that sharpen each other. Disagreement expands the boundaries of inquiry. If everyone accepted the same explanation without question, science would stagnate. When paths diverge, models improve. The truth becomes clearer, not because one side wins, but because both sides force the data to speak more precisely. For you, as a listener settling into the quiet of the evening, the value is not in choosing a side. It is in understanding how science actually works. The goal is not to decide whether Atlas is natural or artificial. The goal is to see the structure of the debate, to recognize that intelligent, experienced people can look at the same sky and draw different conclusions, all while respecting the same rules of evidence. What matters is calm analysis, open-mindedness, and a willingness to follow the data wherever it leads. NASA's voice gives you stability. All current observations are consistent with a cometary nature. Loeb's voice adds dimension. But consistency does not equal completeness. Together, they remind you that the universe is too large, too old, and too subtle for any single interpretation to capture it fully. That is part of the wonder. That is part of the reason you are listening tonight. And it is part of why the next chapter of this story matters even more than the debate itself. To understand why Jupiter matters, we have to understand what Jupiter is. If you zoom out far enough, far beyond the noise of daily news, far beyond the traffic of Earth orbit, far beyond even Mars, you begin to see the solar system not as a set of planets, but as a map of influence. Gravity becomes territory. Orbits become lanes. And one world, more than any other, sits at the center of that invisible architecture. Jupiter. Long before Atlas entered the conversation, Jupiter held the title it still holds tonight. The most strategically influential planet in the entire solar system. If the Sun is the capital of this cosmic landscape, Jupiter is the fortress, massive, dominant, and shaping the orbits of worlds millions of miles away. It starts with mass. Jupiter alone contains about 70% of all the mass held by planets. Out of everything that circles the Sun, Jupiter is the heavyweight. The depth of its gravity well is unmatched. If you could see it the way physicists visualize it, like a landscape, you would see an enormous valley, steep and wide, carved into the solar system's gravitational field. That is why astronomers often describe Jupiter as the fortress of the solar system. Whether you're a comet, an asteroid, or a wandering interstellar traveler, Jupiter's influence shows up early and rarely lets go. Then there is its hill sphere, the region where Jupiter's gravity dominates over the Sun's. For Jupiter, that sphere is enormous, a bubble nearly 52 million kilometers in radius. That's bigger than the entire orbit of Mercury. Nothing else in the system has a gravitational domain this large. It is the biggest territory any planet owns, a kind of natural empire carved out of the Sun's overarching pull. Inside that domain lies one of the most diverse collections of worlds anywhere nearby. Jupiter's moon system is not just a group of satellites, it is a miniature solar system of its own. Io, a volcanic superworld whose surface erupts constantly. Europa, an ocean planet beneath a shell of ice. Ganymede, the only moon known to have its own magnetic field. Callisto, an ancient cratered time capsule. Each one is wildly different, and together they form what many scientists call a complete cosmic laboratory in one place. If you were studying the solar system as an outsider, if you wanted to understand its chemistry, its magnetic fields, its geology, its oceans, Jupiter's neighborhood gives you all of it in a single cluster. But the story stretches even further. Leading and trailing Jupiter in its orbit are two vast clouds of trapped objects, the Trojan swarms, thousands, possibly tens of thousands of asteroids clustered around Jupiter's gravitational balance points, L4 in front, L5 behind. These are rare zones of stability in celestial mechanics, like natural parking lots where objects can linger for billions of years without drifting away. If you were searching for long-term vantage points, or ancient material, or quiet gravitational harbors, this is where you would look. And wrapped around all of this is Jupiter's magnetic field, the strongest, most powerful planetary magnetosphere in the solar system. Strong enough to alter streams of charged particles. Strong enough to interact with plasma tails. Strong enough that anything electrically or magnetically active becomes easier to detect in its presence. This is not just a planet. This is an anchor point, a hub, a command post of gravity, magnetism, and stable orbits. So when you hear that Atlas is aligning with a corridor that leads toward Jupiter's domain, it becomes more than a curious trajectory. It becomes a direction that actually means something. Because Jupiter has a feature few people outside astrophysics ever think about, a wide gravity corridor that allows objects to approach calmly. It is a natural funnel, a space where gravitational forces transition smoothly. If an object wants to pass through the outer solar system without being flung out or dragged inward, this corridor is one of the safest routes. And Atlas, not wildly, not erratically, not chaotically, is heading straight into the edge of that corridor. Imagine the solar system as a strategic landscape. Earth and Mars are small islands. The asteroid belt is a shifting frontier. But Jupiter? Jupiter is the high ground. If you are designing an approach that avoids noise, avoids detection, avoids chaos, and gives you a wide, stable vantage point, you would choose Jupiter every time. That is why tonight's story feels bigger than a simple comet passage. It taps into the kind of thinking that you 40-plus viewers understand instinctively, that positions matter. Terrain matters. Strategy matters. Jupiter is not just a big planet. It is the place where gravitational influence, orbital traffic, and long-term stability all converge. This also explains why the alignment with the keyhole matters so much. The keyhole sits right on the boundary where the Sun's pull and Jupiter's pull nearly balance, a delicate point, a doorway, a threshold between two gravitational empires. If Atlas passes through that threshold, even loosely, it enters Jupiter's sphere of influence in a measurable, predictable way. And the data we have, the straight line drift, the minimal noise, the razor-thin anti-tail, feeds into the same conclusion. Atlas isn't wandering. It's trending. Jupiter's role becomes clear. It is the perfect destination for a quiet arrival. Carl Sagan once said, "If there is life elsewhere, Jupiter's moon system is a natural starting point. Not because it is inhabited, but because it is rich, complex, and gravitationally central." And as the JPL Dynamics team often summarizes it, Jupiter is the pivot of the outer solar system. This is why your curiosity is justified. This is why the trajectory matters. And this is why a path toward Jupiter is not just a path. It is a choice. But knowing why Jupiter matters is only half the mystery. The other half is the keyhole itself. When people hear the word keyhole, they often imagine something small. An opening in a door just large enough for a sliver of light to pass through. In astronomy, the idea is similar, but the scale is cosmic. A gravity keyhole is a narrow region in space where the gravitational forces of two bodies create a precise, delicate balance. Not a perfect balance, just the right imbalance. The kind that doesn't trap an object, but gently redirects it. For Jupiter, this keyhole sits at the very edge of its enormous hill sphere, the region where its gravity overtakes the Sun's. Millions of miles wide, yet somewhere along that border is a window no larger than a few hundred kilometers. A cosmic doorway, a needle's eye. This is why astronomers call it a keyhole. It is tiny compared to the scale around it, almost impossibly small. And yet, if an object slips through it, the gravitational choreography changes. New paths open. New orbits become possible. It is like stepping from one room into another in a house built out of gravity. To picture just how improbable this is, imagine this. The corridor leading into Jupiter's keyhole is thousands of times wider than Earth. But the target itself, the precise region where forces align just right, is only a handful of hundreds of kilometers across. It's like firing an arrow from Earth and threading it through a moving hoop on a jet halfway around the world. Except harder. Much harder. Because nothing in space just aims for something so small. And yet Atlas appears to be drifting toward that region. This is where the wonder begins. If Atlas enters the keyhole, it does not mean collision. Jupiter is far too large, and the keyhole sits far from its surface. What it means is something subtler and stranger. The planet's gravity could temporarily hold onto small fragments if Atlas sheds material, a kind of brief capture. The object could move into a quasi-orbit, circling Jupiter loosely for a short time before continuing outward. Or it could simply pass through the keyhole and leave faint dust or ice signatures that astronomers could detect weeks later. In other words, Atlas could leave fingerprints. And those fingerprints could tell us what it really is. Why is this so rare? Because hitting a keyhole requires three things to line up with extreme precision: the direction, the speed, and the timing. If any one of these drifts by even a tiny amount, the object misses. For a natural body like a comet, that level of precision almost never occurs. Outgassing alone, tiny jets of evaporating ice usually pushes comets off course by far more than the keyhole's width. Randomness wins. Chaos wins. But Atlas is quiet. Its outgassing is unusually low. Its trajectory noise is minimal. Its drift after conjunction, when it emerged from behind the sun, aligns with the direction of the keyhole corridor. The anti-tail, razor thin and stable, gives clear visual confirmation of the orientation. And the non-gravitational acceleration coefficients fit a pattern that makes the alignment physically plausible. None of that proves anything, but it does make the alignment worth watching. If you want the simplest picture, imagine a pebble floating down a stream. The current splits around two stones, leaving a narrow channel in the middle. The pebble has to drift perfectly into that channel, not because it aims, but because every push, every swirl, every tiny influence adds up in just the right way. That's the keyhole, the flow of gravity converging at one improbable place. This is why the idea captivates people, not because it implies intention, but because it is beautiful. A natural alignment that is both improbable and mathematically perfect. A doorway that almost no object finds by accident. An ESA orbital analyst put it best: a keyhole passage is improbable, but not impossible. And impossible is not what astronomers watch for. They watch for the improbable, the outliers, the events that happen once in decades, the ones that make you step outside on a December night, look at the sky, and wonder what stories are unfolding above you. Because if Atlas threads this needle, even loosely, we won't lose it into the darkness right away. Jupiter may hold on to clues: dust, brightness variations, changes in spin, that reveal something no telescope on Earth could capture alone. For the first time, we might be able to watch an interstellar object interact directly with the gravity of another planet. No artist's illustration, no simulation. Real data, real history. And that possibility, that sliver of maybe, is what fuels curiosity tonight. A doorway only a cosmic sharpshooter could hit, and yet the trajectory we're seeing is drifting toward that doorway with unusual calm. But Atlas isn't the first unexpected visitor. The pattern actually began years ago. For most of human history, the night sky felt static. Stars held their places, planets traced gentle arcs, comets came and went according to long, patient cycles. The solar system seemed like a quiet neighborhood on the edge of a vast cosmic plain. But over the last 8 years, that image has shifted. Slowly at first, then unmistakably. Because in just 8 years, 3 objects from outside our solar system have flown through our cosmic backyard. 3 visitors, 3 outsiders. And before 2017, we had seen exactly 0. The pattern begins with the one that changed everything. Oumuamua. Detected in 2017, it was the first confirmed interstellar object in recorded history. Nothing about it was normal. It had no tail, no coma, no dust shed. It moved with a strange, non-gravitational acceleration that no single explanation fully resolved. And its shape, whatever it actually was, refused to match any known natural form. Some models said cigar-shaped, others said pancake flat. The object itself never revealed the answer. It simply spun, brightened, dimmed, and left. This was when Avi Loeb made his now famous argument. Maybe technological. Not in a sensational sense, but in a scientific one, asking whether its behavior matched anything humans could build. Half the scientific community disagreed. The other half wasn't so sure. What mattered was that the debate began. For the first time, astronomers had hard data from something that did not come from our own star system. 2 years later, in 2019, another interstellar visitor arrived, Borisov. Unlike Oumuamua, Borisov behaved much more like a conventional comet. It shed dust. It formed a bright tail. Its composition was shockingly pure, crystalline grains untouched since their birth around another star. And yet, even Borisov surprised researchers. Its tail was too clean. The dust appeared unusually uniform, as if the object had never experienced the violent mixing that most comets endure. If Oumuamua was an enigma, Borisov was a pristine time capsule, an interstellar relic in near-perfect condition. This was the second data point, the second guest. And now, in 2025, the third visitor has arrived, 3I Atlas. And it doesn't match either of the first two. It has a tail, yes, but the tail is too clean. It forms an anti-tail, but the anti-tail is too thin, too long-lasting, too stable. Its trajectory fits a natural model, but the fit is too straight, too quiet, too low noise for an active object near the sun. It behaves like a hybrid, not as dusty and chaotic as Borisov, not as silent and smooth as Oumuamua. Something in between, or something entirely apart. 3 objects, 3 wildly different personalities, 3 interstellar messengers that each tell a different story about where they came from. Statistically, this raises questions. The solar system went billions of years without any known visitors from other stars. Then, within a single decade, 3 of them arrive, each with characteristics that challenge the template. One explanation is technological, that our detection tools have improved dramatically. Pan-STARRS, Gaia, LSST. These next-generation surveys are simply catching objects we would have missed before. And that is partly true, but astronomers are also beginning to consider another possibility, that our solar system sits near one of the galaxy's dynamic crossroads, a region where streams of interstellar dust, rock, and debris flow more densely, a place where material from the Orion Arm sweeps past in long cycles. If so, interstellar objects may not be rare at all. We just started noticing them during a moment when the cosmic tides are pushing more of them our way. This doesn't imply anything technological. It simply implies motion, that the galaxy is active, that the space between stars is not empty, that the solar system is drifting through a region rich in material from other origins, a kind of interstellar migration highway. But even within this broader pattern, Atlas stands apart. Oumuamua was silent. Borisov was classic. Atlas is disciplined, structured, balanced in ways that neither fully natural nor fully anomalous comets usually are. If the first two visitors set the stage, Atlas disrupts the script. It breaks the pattern rather than continuing it. Not by doing anything dramatic, but by behaving in a way that seems too organized for its circumstances. 3 interstellar objects in just 8 years. Something the solar system hasn't seen in billions. That alone is enough to make anyone sit up and pay attention. But it's the differences between them, not the similarities, that make the story worth following. As Avi Loeb put it, we are in a new era of interstellar messengers. And as an ESA scientist said more cautiously, 3 visitors don't make a trend, but they make a question. And that question becomes even sharper when we look at the universe as a strategist. When people think about strategy, they imagine politics, military maps, or business decisions. But strategy doesn't belong only to humans. In the universe, gravity creates a landscape of its own, a terrain shaped not by nations or borders, but by mass, momentum, and time. If you zoom out far enough, you begin to see that the solar system isn't just a collection of planets. It is a strategic map, a terrain of deep valleys, high plateaus, and narrow passes, all carved out by gravity. This is the beginning of what some astronomers casually refer to as cosmic strategy. Not because the universe has intentions, but because its structure naturally creates positions of advantage and pathways of influence. Planets, moons, and gravitational thresholds behave like geographic features on a grander scale. In this framework, the sun is the capital city, the center of mass, energy, and authority. Everything orbits it, everything answers to it, and everything depends on its presence. Jupiter is the high ground, the great fortress on the frontier. Its gravity well is so deep, so wide, that it shapes the entire outer solar system. Earth, by contrast, sits on mid-ground. Stable, habitable, strategically comfortable, but without the commanding influence of Jupiter. Once you see the solar system this way, something surprising becomes clear. Space has choke points. Just as mountain passes control access between valleys, the universe has regions where motion becomes easier or harder depending on alignment, speed, and position. These are the Lagrange points, L1 through L5, gravitational pockets where forces cancel perfectly enough for spacecraft, dust, and even small asteroids to remain balanced. They are the footholds of cosmic terrain. Then there is Jupiter's keyhole, the gravity gate, sitting on the edge of the planet's Hill sphere, a place where an object can, if it arrives with impossible precision, slip into Jupiter's domain through a narrow gravitational doorway. And farther out, at the boundary of the Kuiper Belt, lies the Kuiper Gap, the transition zone between the orderly inner system and the chaotic outer frontier. It's the solar system's outer border post, the line where the sun's influence begins to fade and the galaxy's currents begin to dominate. All of these features form what physicists call natural corridors. These aren't visible lines or roads. They're regions where math favors movement, where objects drift more smoothly, where trajectories stabilize, or where momentum carries something through without dramatic changes. Space is not uniform. Some paths matter more than others, and Atlas has chosen one of the rarest corridors of all. Why is that remarkable? Because nature, especially when dealing with active icy bodies like comets, is rarely that precise. Outgassing typically disrupts alignment. Solar wind pushes unpredictably. Tiny forces accumulate into large deviations. Yet here is Atlas, slipping into a gravitational corridor that most objects miss by millions of kilometers. If the solar system is a strategic map, the Sun holds the center, Jupiter holds the high ground, and Neptune guards the frontier. The orbiting moons, rings, Trojan swarms, and Lagrange regions form the supply lines and outposts. And interstellar objects, rare, unpredictable, and from unknown origins, are the visitors from outside the map, arriving from regions not charted by our gravitational logic. When an interstellar object approaches a strategic position, especially one as narrow and meaningful as Jupiter's Keyhole, astronomers notice, not because it implies anything artificial, but because it is unusual. In geopolitics, a traveler passing through a remote mountain pass would raise eyebrows. In cosmic strategy, an interstellar object aligning with a rare gravitational gate deserves attention. This doesn't mean intention. The universe has no goals, no motives, no desires. But it does have structure. And structure creates pathways. Some paths pull, some paths resist. Some paths narrow into channels so delicate that only the quietest, cleanest trajectory can follow them. Atlas is approaching one of these channels. That alone makes it worth observing carefully and respectfully. This is the philosophical layer behind tonight's story. The layer that speaks to the kind of maturity and depth you 40-plus viewers appreciate. It's the recognition that the solar system isn't random terrain. It is shaped, sculpted, defined by gravitational architecture the way continents are shaped by tectonics. As Michio Kaku put it, gravity is the architecture of the universe. And Carl Sagan added, we live in a cosmos shaped by forces we barely understand. These ideas help us see that Atlas isn't just passing through empty space. It is moving through a landscape. And in this landscape, Atlas is not merely a comet. It is an object entering a rare strategic position. A position that has existed for billions of years, waiting for something to pass through it. That alone justifies watching with curiosity instead of fear, with respect instead of anxiety. Because if the solar system has choke points, and if gravity shapes lanes and corridors the way mountains shape rivers, we must ask a simple question. If these strategic routes exist, why is Atlas using one? And if Atlas is navigating this architecture, how is it adjusting its path so cleanly? There are moments in astronomy when the data is so clean, so quiet, so strangely disciplined that scientists are forced to widen the frame. Not to jump to conclusions, not to make bold claims, but to examine possibilities with calm curiosity. This is one of those moments. Atlas, with its unusually stable vector drift and razor-thin anti-tail, invites a gentle question. What kinds of forces can move an object without leaving a visible trail? We're not claiming anything here. We're simply examining. Science moves by looking at every model that could fit the data and ruling out the ones that fail. When the expected explanations fall short, you don't invent new worlds. You expand your list of possibilities. One of the quietest forms of propulsion ever theorized is the solar sail. A solar sail doesn't burn fuel. It doesn't release gas. It doesn't create a plume or a flash. It lets photons, particles of light, push gently against a large, thin surface. The acceleration is tiny but steady, and if the sail is aligned correctly, the movement is smooth, clean, and directionally consistent. A solar sail can explain a stable vector drift without chaos, a straight path without noise. Of course, no one is saying Atlas is a solar sail. But if you imagine a mechanism that produces force with no exhaust and no turbulence, a sail-like effect is one natural place to begin. Another possibility, still firmly within the realm of physics, is a magnetic sail. A magnetic sail interacts with the solar wind, the stream of charged particles flowing from the sun. It doesn't need combustion. It doesn't heat up. It simply uses magnetic pressure to generate a very small but continuous push. If Atlas contained metallic components or a conductive core fragment, such interactions might subtly shape its drift in ways that appear controlled. And here's the intriguing part. Magnetic interactions wouldn't show up in optical data. You wouldn't see a glow. You wouldn't see a plume. You'd just see a trajectory that adjusts smoothly. Then there are micro-adjustment jets, natural or otherwise. Even something as simple as a consistent vent on one side of the object could create tiny nudges that accumulate over weeks. If the internal structure of Atlas is unusually uniform, or if its surface vents are arranged symmetrically, the resulting acceleration could be clean rather than chaotic. Most comets don't have that luxury. They're patchy, uneven, and messy. But a fragment of a planetary core, metallic, tighter, less fractured, would behave differently. It would rotate with more stability. It would vent more predictably. It would drift more gracefully. Of course, there are purely natural explanations that require no exotic models at all. If Atlas has a dense rocky or metallic nucleus, that would anchor its center of mass more firmly. Heavy dust grains could produce a thin, stable anti-tail that resists dispersion. A perfect post-conjunction geometry could minimize the apparent jitter in its orbit, allowing the trajectory fits to come out clean. None of these require engineering. They just require the right combination of mass, timing, and geometry. So why consider these quiet technological analogies at all? Because they help us describe the shape of the anomaly. They give language to something that feels unusual. A trajectory too smooth for an active comet. A drift too stable for thermal forces alone. Not because we're looking for aliens, but because the scientific method treats every anomaly as an opportunity to test the boundaries of our models. Avi Loeb put it succinctly: if we ignore anomalies, we stop learning. The point is not to overreach. The point is to stay open. NASA's own navigation teams acknowledge this balance. As one JPL analyst recently noted, outgassing can mimic many effects, but not all. When nature produces behavior that skirts the edge of our expectations, the responsible approach is neither denial nor sensationalism. It is exploration. This is the heart of quiet speculation. Wonder without panic. Curiosity without conclusion. You're not asked to believe anything extraordinary, only to acknowledge that precision in any form deserves attention. A propulsion that leaves no trail is indistinguishable from perfect natural alignment. And when the line in the sky is this straight, the beauty lies in understanding why. Whether Atlas is entirely natural or partly shaped by forces we don't yet understand, its movement is elegant. Its anomalies are gentle, not alarming. They whisper rather than shout. And for a moment, they let us stand at the edge of possibility, not because we expect something extraordinary, but because we understand how rare such precision is. And that brings us to the question we rarely ask out loud: why now? If you step back and look at 2025 from far above Earth, not in geography, but in time, you start to notice something subtle. Atlas is not arriving in a random year. This is the year when our tools, our technology, and even the sun itself align to make an event like this visible in a way it never could have been before. The question isn't why Atlas came in 2025. The question is why 2025 is the year we finally see Atlas clearly. The first part of the answer lies in the sky itself. We are at the peak of the solar maximum, the period every 11 years when the sun becomes more active. Solar flares intensify, the corona brightens, and the solar wind grows stronger. For most people, this means little more than spectacular auroras. But for astronomers, a strong solar wind sharpens the signatures of comets and dust structures. Tails become easier to detect. Anti-tails, those delicate, razor-thin dust planes, stand out more clearly against the background. When Atlas emerged from behind the sun, the increased solar activity didn't hide it. It highlighted it. Then there's the wave of new generation telescopes transforming our ability to observe faint objects. The Vera Rubin Observatory, formerly LSST, is preparing to begin its deep sky survey, capable of capturing objects hundreds of times fainter than previous systems. JWST is already rewriting our understanding of distant galaxies, and its sensitivity allows cross-checks on brightness curves that older observatories would have missed. Gaia continues to refine the positions of stars to micro-arc-second precision, giving astronomers the reference frame needed to measure tiny shifts in Atlas's vector. And on the ground, thousands of small amateur and university telescopes now use AI stacking, software that layers hundreds of frames together to reveal structures invisible to standard imaging. This combination means one thing: we are watching the universe with better eyes than any generation before us. And AI has quietly become the unsung hero of modern astronomy, not in a flashy science fiction way, but in the patient, methodical work of data cleaning. AI now removes atmospheric noise, corrects distortions, enhances faint streaks, and predicts motion across blurred frames. We can follow dim objects across nights when, a decade ago, they would have vanished. If Atlas had passed in 2010, we might have seen only a smudge. In 2025, we see its structure, its tail, its anti-tail, its vector drift, all with unprecedented clarity. There's a small philosophical truth hiding beneath this. Atlas didn't suddenly become interesting. We became visible. Not visible to Atlas, visible to ourselves. We reached a level of observational maturity where the universe now reveals details that were always there, simply waiting for us to catch up. We didn't become special. We became capable. Look at the timeline. 2017, Oumuamua. 2019, Borisov. 2025, Atlas. 3 interstellar objects, each discovered in the era of modern survey telescopes. Some scientists argue these objects have always passed through, unseen. Now, the sky is watched 24 hours a day by instruments that miss almost nothing. This means something profound. Atlas isn't the end of anything. It is the beginning of a detection era. In the next decade, we may see many more interstellar visitors, fragments of far-off planetary systems, relics of stellar nurseries, or icy wanderers that cross light years before reaching us. The solar system may not be a quiet cul-de-sac. It might be a crossroads, a gravitational hub where interstellar material passes more often than we used to think. And in that context, Atlas becomes more than a comet. It becomes a signpost, marking the moment when humanity finally gained the tools to watch the galaxy breathe. Neil deGrasse Tyson put it simply: we are finally seeing the universe with the resolution it deserves. And now, let's follow Atlas to March 16th, the day it reaches Jupiter's domain. If you've been following this journey from the beginning, you've felt the slow tightening of the line, the way Atlas has been tracing a path so clean, so steady, that March 16th has turned into a quiet milestone. Not a moment of risk, not a moment of alarm, but a moment of clarity, a checkpoint in the cosmic timeline. On March 16, 2026, Atlas will reach its point of closest dynamic interaction with Jupiter. Notice the phrase, dynamic interaction. This is not a collision course. Jupiter is enormous, a world so large that if Atlas were heading directly toward it, we would have known months ago. Instead, the comet will pass far outside Jupiter's physical body. What matters is not distance, but influence. For a brief window, Jupiter's vast gravitational field will nudge Atlas in a measurable way. Gentle, predictable, safe. From that interaction, 3 outcomes are possible, all calm, all grounded in physics. First possibility, Atlas simply passes the outer edge of Jupiter's hill sphere and continues onward. Most interstellar comets do exactly this. They drift in, feel a small sideways tug, and sail back out into deep space. In this scenario, Atlas would remain almost unchanged. Its trajectory would curve slightly, but nothing dramatic would happen. This is the most common path. Second possibility, Atlas enters the gravity corridor, but misses the keyhole. This would cause a more noticeable redirection, sending it on a new outbound path shaped by Jupiter's pull. Nothing dangerous, just the natural scattering effect that giant planets have on stray objects. Atlas would spend years or decades drifting outward, slowly fading from our instruments until it rejoins the interstellar dark. Third possibility, the rarest one. Atlas glides through the keyhole itself. This is the scenario that fascinates astronomers, not because it's dramatic, but because it's informative. Passing through the keyhole doesn't pull Atlas into Jupiter. Instead, it allows Jupiter to exert a very specific gravitational influence. If Atlas sheds even a few grains of dust, those grains could be temporarily captured, orbiting Jupiter before dispersing. They would become samples, natural specimens stored briefly in Jupiter's domain, ready for long-distance study through reflected light or spectral signatures. It's not a threat. It's an opportunity. Why does this possibility hold so much interest? Because the way Atlas is approaching Jupiter is tidy, unusually tidy. Its trajectory is cleaner than expected. Its drift aligns with the corridor. Its anti-tail suggests a stable orientation. None of this guarantees a keyhole passage, far from it. But it makes the alignment worth watching with the same quiet concentration you would bring to a chess match. Not for the drama, but for the strategy. And what will we actually see on March 16? Not a spectacle, not a bright flash or sudden change. Instead, astronomers will measure incredibly small shifts in Atlas's motion, tiny deviations in brightness, subtle changes in angle, a slight adjustment in speed. It's a scientific moment, not a cinematic one. The kind of event that rewards patience rather than adrenaline. The meaning of the moment goes deeper. If Atlas hits the keyhole, our models of interstellar dynamics gain a rare data point. We learn something new about how objects migrate across gravitational domains. If it misses, we still learn, because Atlas will become one of the cleanest examples of near keyhole alignment ever recorded for a natural body. Either way, this is not a moment to fear. It is a moment to witness. A moment when the universe whispers instead of shouts. A moment when precision is the entire story. Because March 16 isn't about danger. It's about the elegance of gravitational geometry. The way a distant, icy traveler interacts with the deepest well of the outer solar system. It's a reminder of how lucky we are to be watching this unfold with modern tools, patient minds, and a sense of perspective that comes only with time. For you, sitting back and listening, this moment is meant to feel peaceful, grounded, like observing a rare bird migrating through a valley. Something quiet, fleeting, and profoundly natural. You don't brace for impact. You simply appreciate the rarity. And as the JPL Dynamics team said, a keyhole passage is a scientific gift, not a threat. But to appreciate March 16th, we need to return to something deeper, the feeling behind all of this. As we move toward the end of this journey, the pace begins to shift. The intensity fades. The sharp edges soften. Because what you've been listening to tonight is not a warning. It's not a threat. It's not a crisis to brace for. It's a window, a rare and beautiful one, into a universe that is vast, mysterious, and profoundly calm. And the feeling you carry now is meant to be the opposite of fear. There is a quiet truth at the heart of astronomy. Fear and awe are not the same emotion. Fear is what rises when the mind imagines threats that are not there. Awe is what appears when you stand before something immense and realize it doesn't want anything from you at all. Atlas lives entirely in the second category. It does not menace. It does not intrude. It simply moves with a grace that invites you to breathe a little deeper. In that way, Atlas becomes a gentle lesson from the cosmos. Not a message, not a sign, just a reminder. For all the talk of trajectories, gravity corridors, and keyholes, nothing Atlas is doing poses danger. It does not break anything. It does not disturb anything. It is a traveler moving through a landscape that existed long before us and will exist long after. The strangeness in its path is not a warning. It is an opportunity to witness something rare. And we are the lucky ones who get to see it. Think of how many generations lived and died without ever knowing that objects from other star systems pass through ours. Think of how recently we gained the tools to see razor-thin antitails, micro-adjusted trajectories, or the delicate balance of a keyhole passage. Even 30 years ago, Atlas would have been a faint dot, a footnote. Tonight, it is a story, not because it has changed, but because we have changed. That is the soft power of wonder. So let your mind settle. Let the tension of unknown outcomes dissolve. Because the truth is simple. The universe is not against you. Jupiter is not against you. Atlas is not against you. Everything you've heard tonight, every shift, every vector, every possibility is happening hundreds of millions of miles away. Quietly, predictably, according to the same laws of physics that have kept Earth safe for billions of years. Even the strangest paths in the heavens are governed by order, not chaos. Sometimes it helps to step into a different perspective. Curiosity is not stress. Curiosity is health. It's a sign that your mind is awake, engaged, connected to the bigger world beyond your daily routines. When you observe the cosmos, even passively, even through a voice in your ear, you participate in a human tradition older than every civilization. You become part of the lineage of people who looked up and wondered rather than feared. This is why mystery is not the opposite of safety. Mystery is the companion of safety. It is what makes the quiet moments richer. Atlas shows us that the unknown can be gentle, that something unfamiliar can still lull you toward rest, that a visitor from another star can bring peace instead of alarm. And in the softness of that realization, tension melts. Shoulders drop. Breathing slows. The mind stops trying to prepare for outcomes and begins simply receiving what is. Tonight, you are not bracing for anything. You are arriving, slowly, steadily, at a place of calm recognition. All scenarios are safe. All outcomes unfold far beyond Earth. All movements of Atlas are just expressions of orbital mechanics, nothing more. You are witnessing subtlety, not threat. Precision, not peril. So as we move toward the closing moments of this journey, let your inner landscape widen. Feel the weight of gravity only as grounding, not pressure. Let the mystery of the night sky feel warm instead of cold. Let yourself drift into the sense that everything is okay tonight, because it is. Carl Sagan once said, "We live in a universe that is not hostile nor benign. It is simply indifferent, and that is comforting." Indifferent, not in a cold way, but in a way that frees you. The cosmos has no agenda against you. And that means you are safe to rest under its vastness. And now, let's close the night the way the universe closes every day, quietly. As this long, gentle journey comes to an end, picture the sky one last time tonight. Atlas, once bright and sharp in the headlines of your mind, is now drifting farther from view. Its coma is dimming, dissolving softly into the background darkness. Its light is no longer a question to solve, just a faint memory moving peacefully along its path. And beyond it, Jupiter hangs like a muted lantern. A giant, silent silhouette against a tapestry of distant stars. Nothing loud, nothing dramatic, just presence, just gravity, just the calm heartbeat of a world that has shaped the outer solar system for billions of years. This is the scene as we close the night. You've traveled far with Atlas, farther than most people ever will in their imagination. From the first anomaly to the thin, impossible anti-tail, to the idea of a gravity keyhole, to the brightness peak of December 19th, to the gentle, inevitable approach toward March 16th. Every step has been strange, yes, but also beautiful. Beautiful because it was real, not dangerous. Beautiful because it reminded you that even the unknown can move softly. And in that softness lies the heart of this outro. There is a question behind every cosmic story. Should we fear the unknown? It's natural to wonder, natural to imagine danger in what we don't understand. But tonight has shown you something different. The unknown is not automatically a threat. The unknown is simply that, unknown. A space waiting to be filled, not with fear, but with understanding. Fear and respect share the same root. They begin as the same instinct. But fear freezes the mind. Respect opens it. And tonight, you chose respect. Atlas never aimed to harm. It never threatened Earth. Every movement took place hundreds of millions of miles away, playing out across a stage so vast it makes human worries feel small. Not insignificant, just lighter. Everything Atlas has done, every curve in its path, every shift in its brightness, has been governed by the same elegant physics that keep Earth safe, stable, and warm. And you, sitting here, listening, are alive at exactly the right moment to witness a visitor from another star pass quietly through your solar system. That is not something to fear. That is something to feel grateful for. Out of all the possible generations, all the possible centuries, you are here, now, with eyes and instruments capable of seeing what no one in human history could see before. Let that feeling sink in. A sense of smallness, yes, but a special kind of smallness. Not weakness, not insignificance, but smallness as in part of something vast, part of something ancient, part of something calm. You are connected to the universe, not by force, but by observation, by curiosity, by the simple act of looking up. Now your breathing can slow. Your shoulders can drop. Let the thoughts that were sharp earlier in the night begin to blur at the edges. There is nothing you need to prepare for, nothing you need to guard against. Everything in the sky is following its orbit, predictable, steady, serene. The universe isn't dangerous. The universe isn't chaotic. The universe simply moves, slowly, beautifully, without rushing for anyone. And tonight, you get to rest inside that rhythm. Feel your body settling. Feel the weight of the day slipping away. Feel the quiet of the cosmos folding gently around you like a warm blanket. You are here, alive, witnessing a visitor from the stars. Let that thought be soft, not overwhelming. Let it be the final warm ember as the mind quiets. Mystery is not the opposite of safety. Mystery is the soft space where safety and wonder meet. Somewhere out there, Atlas drifts into the dark. Somewhere farther still, Jupiter continues its silent orbit. And beyond them, the stars hum the same quiet song they have always sung. Nothing demands your attention now. Nothing is calling you to stay awake. Everything is easing in the same direction, toward rest. Brian Cox once said, "The universe is more reassuring than we think. It continues, with or without our fears. And that is the comfort you take with you into sleep. The night is wide. The stars are steady. Your world is safe." and the universe is still quiet tonight. Sleep well. The stars will keep watch for you.